Okay, so some matrix information. Matrices are always labeled with what we call an order. In this case, the order of A is a 2 by 3, and it's the number of rows, so like 2 rows, 3 columns. So this is a 3 by 1. This is a 2 by 2. Yeah. And then if you're going to name the actual elements of a matrix, you name them like D11, D12, D, etc. So like this element right here would be A1, 2. And I mentioned this, I think, in class. You don't always have to put a comma. If it was like A4381, because you had a gigantic one, then yeah, it would be nice. Put the comma there. But most mathematicians are fairly lazy and would probably avoid adding a comma here, and that's not super big deal. Okay. Cool. Moving along. So why do we ever even use matrices? Long story short, mathematicians are lazy and matrices are quick and easy to read. Here's an example for why you'd actually have a matrix. You could think about it as really a matrix is basically a real life spreadsheet. So let's say you own a coffee store and you've sold coffee, tea, and hot chocolate, and these are your sales in January, February, and March. This is just like the spreadsheet that you would use, and in this case we call it a matrix. If you're using things like Excel or Google Sheets, you're basically dealing with matrices. Okay, adding and subtracting matrices. Super important, they have to be of the same order. So this right here is a 2 by 3, and this is a 2 by 3. And in this case, all you do is you would take the elements that are in the same position, you would add them, and you would put them in the final position. So 6 plus 2 is 8. By the exact same thing, if we had like this one, 0 plus negative 3 is negative 3, that would go here, and then the rest of them would fill in the same way. Just like that. If you were subtracting, it would be the exact same idea, except instead of 8 plus 4 is 12, you'd say 8 minus 4 is 4, and 0 minus negative 3 would get you a positive 3 here. So same idea. But they do have to be exactly the same order. So in this case, I can't do this because you would probably start and you'd match up and say, okay, well, the 2 and the negative 2 can pair off, the 4 and the 5, but then all of a sudden you're like, hang on, what do I do with this 3? What do I do with these numbers? And it doesn't match up, so if they're not the same order, it's not possible. So this right here is not possible. Have to be the same order. Moving along. Scalar multiplication is like if I take this matrix and I want to scale it up by 6, you would just multiply every single element in here by 6. So in this case, you'd get 30, 0, negative 18, 12, 6, and 54. This number, by the by, could be any old thing that you wanted to. It could be a negative, a fraction, or whatever, and it is called a scalar, which just basically means you're scaling up or you're scaling down. So this is now 6 times larger than this. Again, moving on. Okay, matrix multiplication. I'm going to show you how to do it here, but I'm going to explain what it would get you here. So this is that same matrix from before. We've got coffee, tea, 3 months. This could be like the cost of the coffee. And what's going to happen is as I'm multiplying these, I would end up multiplying the $2 cost of the coffee by the cost of coffee in January. I would multiply that $1 cost of the tea by the tea in January. And then the 50-cent cost of the hot chocolate for the number of hot chocolates that you sold in January. And you'd end up with a total for how much money you made in January, how much money you made in February, how much money you made in March. Okay, so let's move that out of the way and then let's show you an example of how to multiply. Okay, when you are multiplying matrices, what you're going to do is you are going to start by kind of comparing the rows and the columns. So in this case, what I would use is I would use this row, AB, and I would compare that with the row here, EG. And what I'm going to start with is I'm going to get A, oops, wrong thing, sorry, A and B, E and G, and I would add them together. So first you take A times E, and then you would add to that B times G, and that is what's going to sit in this top column. And notice I use the top row, or I use the first row, and I use the first column, and notice this position, it is in the first row and the first column. Okay, so to get this one down here, I'm going to use the second row and the first column, and then that final answer is going to end up right here, because this right here is the second row in the first column. So to get this one, I would have C times E plus D times G. Same way I would get the other ones. So to get this position up here, what I would be using is the first row and the second column, and that would get me this position right here, because it's the first row and the second column. So I would get, in this case, AF plus BH, so A times F plus B times H, and then of course the last position to get this second row and second column, I'm going to use the second row and the second column, and I will get CD plus DH, or CF plus DH. Okay, so let's do one more example. Okay, let's go through this, and then I will kind of talk about a little bit about the orders of these. So here I have a 2 by 3, and here I have a 3 by 2, and that is actually going to work out for us. In this case, to get this number right here, I'm going to write this kind of above, so this is our goal number right here. We're going to get that number right there. What we're going to end up doing is we're going to do 1 times -1 plus 2 times 7 plus 3 times -2. So we're going to evaluate this whole thing. So I did this 1 times -1, 2 times 7, 3 times -2. And since that's the first row and the first column, that's where this is going to go. First row, first column. That's where we're going to end up. If you evaluate this, you get -1 plus 14. That gets us 13. Plus a -6 would get us down to 7. So our final answer here is going to be 7. Then again, and I'm not going to write it all out here, but we'll kind of go through it. Here we'd have 1 times 0, which is 0, 2 times 9, which is 18, 3 times -3, which is -9. So I have an 18 and a 9 that I'm going to, or a -9 that I'm going to put together. And so that would also give us here a +9. Then we'd have 4 times -1, which is a -4. 5 times 7, which is 35. 6 times -2, which is -12. If you add these together, you will get 19 right here. And then for this last one, we're going to have 4 times 0 plus 5 times 9 plus 6 times -3, and you'd get 0 plus 45 plus -18, which gets us 27. Okay. So hopefully we're starting to get an idea of how to multiply these things together. Now let's talk a little bit about the orders. So for the orders, what we're going to do is, let's look through. So this one right here, we had a 2 by 3, and here we have a 3 by 2, and our resulting one was a 2 by 2. In order to multiply, this number and this number must agree. If they're not the same number, then it's not going to work. It's super important. So these must be the same. And then these two numbers end up giving us our resulting matrix. So let's go through a little bit about which ones can and which ones can't I add together. And really what we're asking right now is matrix multiplication commutative. Commutative just means that, like, if you have 8 times 5, that is the same thing as 5 times 8. So the question is, if I have a matrix A, which is maybe 1, 0, 0, 1, And matrix B, which is, no, let's not do that. Let's do 3, 1, 4, 2, 8, 9. So this is a 2 by 2, and this is a 2 by 3. Can I multiply these together? And it turns out you can do A times B. That's totally okay because these two numbers agree. But can you do B times A, where you'd have a 3 by 2 times, or sorry, a 2 by 3. Switch the numbers, can't do that. A 2 by 3 multiplied by a 2 by 2. And the answer is no, you can't do it. So let's go through these examples quickly. Can I do this? Okay, so what we're going to do is just ask, is this even possible? And if it is, what's the size of the resulting matrix? And what you need to look at is really, do these two numbers match? So is this one possible? Yes. And the resulting matrix, I will tell you, is a 2 by 6. Is this one possible? 4 by 1 times a 1 by 2. Also answer is yes. And the answer for what will the resulting matrix be is a 4 by 2. Is this one possible? Also yes. Look at all these yeses that we have. And in this case, the resulting matrix is a 2 by 2. Here, and in this case, notice what I did was I just switched them back and forth. So is it possible that you could switch that A times B? So like, are there existing cases where this is an okay thing? Yes, it is possible for you to actually end up with the same thing. But, so yes, I can do this. But in this case, my answer is going to be a 3 by 3. So I want you to note that like the answer that I got was very different. So even though I can take this 2 by 3 and multiply it by a 3 by 2, and then I could switch the order, the answer, I got a totally different matrix when I ended up with the end of it. So careful with that. And then here, if I have a 2 by 3 times a 2 by 3, the answer is no, I can't do it. There's just no way to multiply them together. Hopefully that helps clarify a little bit. Okay, the last thing is the multiplicative identity, which is basically if I have some matrix A, what can I multiply it by to get that same matrix A? And in just like regular numbers, it's just 1. So 8 times 1 is equal to 8. And it turns out in this case that it's actually pretty similar. The matrix you would multiply by is this. And it's really important that we understand, first of all, that, so here this is a 2 by 2 matrix, and I wanted to end up with a 2 by 2 matrix. So that kind of tells you what you have to have for how big this matrix has to be. So in this case, I know that this number and this number have to match, so it's going to be a 2. And because I want to end up with a 2 by 2, I know that the second number also has to be a 2 by 2. So in this case, if you multiply these, you will actually get the same matrix back. And it doesn't have to be a square matrix to start. So here I have a 3 by 2. So a 3 by 2 is going to multiply by something, and I want to get out a 3 by 2. Well, since this number is a 2 right here, you know that it's going to be a 2 here. And since this number is a 2, we also know that the second one has to be a 2. So it turns out that this one is actually going to have the same identity matrix, and it will get us our original matrix back, which let's just double check here that that's working. Negative 6 times 1 plus 0, sure, that gets us negative 6. Then negative 1 times 0 plus negative 1 times 1, hey, that gets us, or sorry, negative 6. I did that wrong. Negative 6 times 0 plus negative 1 times 1. That would get us negative 1. And if you keep going through, you're going to end up seeing that you get the exact same matrix out. And it doesn't, again, it does not have to be square. In this case, if I have a matrix that is literally a 1 by 5, it will work. You're just going to get a 5 by 5 matrix that you're going to end up multiplying by, and that matrix is going to be this one. So it just has to have those ones kind of down the diagonal. And somebody asked in class, okay, cool, great that we can have these and like get the same matrix out at the end, but why would I do that? And the best answer I can give you right now, we'll have better answers later, is that you guys have been multiplying by 1 for a long time. You had a problem on your check-in that looked like this, and it said simplify, and you were like, oh, well, I need to multiply by this fancy 1 here. So I'm going to do 1 minus I, 1 minus I. And this was actually multiplying by 1 is how we solved this problem. Similar things are going to work out with the identity matrix here, so just roll with me that it is actually important. Okay, let me know if you have questions. Hope that helped out. Have a good day.